And welcome back to Fullerton College Prepress. This is Professor Ben Hewitt, and today we're going through the PIA's Prepress Training Manual, Chapter 4.2, Task 4, Module 2, Color Reproduction. This is another one of those ones that I really like. I'll try not to go on too long, but this is one of those topics that I find utterly fascinating, and a thorough understanding of this topic is really one of the things that can set you apart as a prepress person between a newbie, an amateur, and someone who really knows what they're doing. This is the difference between good and great, is understanding this type of stuff. Scroll with me. So what the PIA would like you to know is be able to understand the separation and filtration principle as how scanners and cameras will pick up color, and then differentiate the idea of halftone from continuous tone, and understand the number of colors that can be reproduced in various image formats, because it varies. We also want to look at tone, gray balance, color correction, and understand how these change the color reproduction process. And lastly, we're going to go into talking about UCR and GCR, because what's life without a few TLAs? That's my joke. TLA stands for three-letter acronym, hee hee. Each one of these does a different distinct thing and does different things. No. Sorry about that. I had a walk return to my house with the dogs, my girls, and my wife all showing up in the middle of my recording. So I had to pause and it threw me off for a minute. Anyways, UCR and GCR, we're going to talk about what they do, why they do it, how they do it, and what does that mean for your reproduced image. First off, here we are to talk about reproduction. In this case, we're not talking about how we make more humans or why there's more cows in the farm every spring. At this point, we're talking about making copies, which is also what happens in reproduction, biologically speaking. When you have a child, I now have had two, so I understand this a bit, you are not building a clone, although sometimes it does feel a little bit like that, especially when they're doing the annoying things that you do. You're like, ah, man, I'm so annoying. But anyways, that's a joke, I swear. The point is, when you make kids, when you have children, you're not making a clone. You're not building an exact copy of yourself. You're making an approximation, divided by the other person involved in the process. When you're talking about human reproduction, when you're reproducing artwork, you're not reproducing an exact copy. You're making a good match. You're making a version of it that looks like it and has a lot of the same characteristics as it, but you're not making the exact same thing. I mean, if you want to just take it to the extreme and think about it with artwork, capital A, if you're talking like famous paintings that are being reproduced as images in books, obviously they're not going to resurrect Leonardo da Vinci and have him repaint his painting millions of times for each copy of a textbook on art history. That doesn't work. You can't do that. And even they don't have someone else repainting it. No, they take a photo of it and they turn that into a printing information, and they print that into the textbooks to show you Leonardo's paintings. So a color reproduction system is a system that allows you to capture and recreate similar colors to what you've seen originally. As we've kind of talked about in color appreciation last chapter, obviously it cannot be an exact match and it has to be a reproduction, because unless a color is reproduced using the exact same materials, it will not be the same in all viewing conditions. So just by having a photograph of a painting is already going to look different than the painting, because the actual real physical pigments in that painting, in the original paint, is going to be different than the pigments and dyes used in a photographic print, which are going to be different than the 4-color printing process that we're going to use now. Anyways, so to understand these things, we're going to start at the end and work backwards. There are 3 different color reproduction systems in use here. The camera that takes the picture is a color reproduction system. It sees light and it records it in the way that it records it, either on film chemically or using electronic sensors digitally. Then there's off-press proofing, because as we'll talk about later, you don't often run a proof on the actual printing press unless you're doing digital. A proof will be on a different system because it's not workable to build it, to make all the plates, align all the plates, bring the press up to color to print one copy and ask the customer, hey, does this look good to you? That's costly and wastes a lot of time. So proofing happens on a different system, often a digital or an inkjet that is calibrated to look a lot like it, and the press itself. But all three of those systems seek to reproduce color, and they all do it in their own way. And the real trick to color reproduction, and indeed color management, is getting all of these systems to agree. So as I champion in general, and I did even before I started teaching from the PIA curriculum here, you really need to start at the end and work backwards with a lot of printing processes, because you can't just start and see where it takes you. That leads you to nowhere. You need to start at the end and work backwards to figure out what you're doing. So starting at the press, the last thing that happens is a printing press puts ink on the paper and produces the actual final output. Before that, it's been proofed. So the CMYK colors need to be tested and approved by your client before you run millions of copies on offset presses, or worse, or better, depending on how you want to look at it, or better, something like rotogravure, or something that costs more and takes more time and effort. Before you go into that, you want to get them to approve it. So you make a proof and you show them what it is probably going to be like, and they sign off on it saying, yes, this is close enough, or I really wish you could do better with that red. Typically red's not the problem. Blue is. But anyways, the proof that has to be tested on a proofing device to prove that it's going to work. Before that, the image has to be captured on a camera. We'll just say it's all digital at this point. We're not even going to go with the extra step of a film camera and developing the film and scanning it. Yeah, let's just go for digital. Assuming you're shooting on a digital camera, the images that you want to have in your printed document all have to be captured digitally. They'll have to be captured in RGB mode, because a camera, digital camera specifically, attempt to be an artificial human eye. Just as we have red, green, and blue cones in our retinas that sense the different levels of light, so a camera has red, green, and blue filtered photoreceptors in its sensor to try and capture things the way we see them. Because you could also use a film-based camera and then scan it. But either way, that ends up with RGB data, because RGB is the colors of light. That's additive color, remember? And before that, you have a person, the Mark I human eyeball, the most accurate color system that we know of in the world. Yes, I'm a little full of myself for my own species here. To anyone who's not human, I apologize. Of course, I think human vision's the best. It's what I have, and I have literally no way of comparing it. But anyways, everything is, we're trying to reproduce what a human eye sees. I know it sounds a bit Orwellian, that all that really matters to us is convincing other humans and tricking human eyes. But until we establish some sort of trade or communication with visual-based mediums, with aliens or even creatures on our own planets, before we try to read and write and send books and magazines back and forth with dolphins and dogs and elephants are pretty smart, we don't need to care how they see. All that matters is, to a human observer, is this a passable thing? Does this likeness make a human respond to it as though we're looking at the real thing? The difficulty here is every step we went backwards, if you go forward in time, each step loses color. I posted a separate video on gamuts and what that means, and it has a really cool visual showing you what types of things are available. And we've actually charted this too. And when we get into talking about LAB color, we'll definitely talk about charting human vision, because that's a really exciting topic. But every step of the way, human eyes see the most amount of color that we're able to understand. If anything sees more color than us, we have no way of understanding what that is. We are limited. So to us, the very limits of what is possible is what we're able to observe with our Mark I human eyeballs, which do a pretty darn good job. We built cameras to mimic our eyes. They're not as good as our eyes. I know it's easy to get into the trap, especially if you've been doing graphic design for a while, of just thinking about how, RGB contains all the colors and CMYK dumbs it down and you can't hit all the colors. But honestly, RGB is already missing the mark. There are already many colors, many tones that are impossible to reproduce on a monitor, even though that seems to be a better way of making color. So the human eye sees more. The camera sees less than that. The proofing press is able to produce some of the colors that the camera sees, and the final actual printing press produces the fewest possible colors and has to compress everything that our eye sees down to just a little amount of what it can do. So we're going to talk a little about the separation process, because we want to see how does the image data that our cameras or scanners, well, scanners are more rare now, capture, how is that translated into the halftone dots that have to get printed on paper, and why? Let's take a look at this. So, a color separation, every image that you get has 3 channels. Sorry, every RGB image that a camera or scanner takes. 3 channels for the 3 primary colors, which really in the end are really just charting our own vision system for our cone colors, the red, the green, and the blue. So you have the channel, which is how the picture looks if you only count the red light. That's why it's in black and white there. The green channel, if you only have green light, what does it look like? And the blue channel, if you only are looking at blue light, what do you see? So in each one of these, it's a diagram. The brighter the white in those channels, the more of that color you're seeing. Because remember, it's additive color. It starts with darkness, and then it adds color. The less that you see of that color, the darker it is. That's why if you look in the 3 channel pictures, look at it's a covered bridge, but I still call it a barn sometimes. Look at the red barn in the color image down below on the red channel. That's nearly white. On the green and blue channels, it's pretty dark. The big tree that's kind of a dark green is near completely dark on blue, pretty dark on red, and only bright on green. And that white fence is white in all 3 channels, because remember, if we see an equal amount of red, green, and blue light, to us, that is white. So separation. Each channel also carries cyan, magenta, and yellow required. If you think about it, remember that cyan is the opposite of red. Cyan ink filters out red light, magenta ink filters out green light, and yellow ink filters out blue light. Therefore, whatever is dark in the red channel becomes sorry, I'm tripping over my words here. The darker parts, the black parts of the red channel are more intense cyans. The darker parts of the green channel are magentas, and the darker parts of the blue channel are yellow. And that works out pretty well if you think about it. But anyways, as you look at the different things. So yeah, cyan ink is not going to have a whole lot of ink printed on a red barn bridge thing, but there'll be a lot of magenta and a lot of yellow. So you can see on the magenta and the yellow ones, those end up turning out fairly brighter. I'm going to actually have you guys try this out in a project. Apologies to the 2 of you, or maybe more. I only remember 2. Uh-oh. Now it's in my video, that have been through my color management class. If anyone has been through my color management class, you may have done something like this before, but it's okay to do it again. We're going to actually do this using Photoshop. We're going to create our own color separations. It's fun, I swear. So the RGB gray values are converted into the equivalent cyan, magenta, yellow, and black halftone dot values. The cyan, the magenta, and yellow, again, we're using our halftone dots there. Halftones we'll talk about more later as we get into it, I promise. And then there's also the black separation. And this is calculated through all 3. If anything is dark in all 3 channels, red, green, and blue, it must then therefore add that 4th color, black. This has to do with the fact that in cyan, magenta, and yellow ink are not dark enough, not pure enough, and not intense enough normally to be able to print without a 4th color. However, some of us who have seen this, and if not, take my word for it, the HP Indigo press has such intense inks that it's capable to print 3 color and make it look like 4. I have some samples in our print lab. Whenever we're able to see them, a video in the lab wouldn't show it because it just wouldn't have the gamut to show those differences. But they are capable with some very high-end, very expensive presses with proprietary ink to forego a black separation and print with just the 3. But typically speaking, you need black because the cyan, magenta, and yellow aren't dark enough. You add them together and you don't get black, you get asymptotal black. You get kind of black-ish, and it's really more of a muddy gray. It's just not quite there. We're going to talk a little bit more of that when we come back. Thanks for listening. This was part 1. Stay tuned for part 2.